Gareth Owen. GCHQ recently published a code on the internet for potential job applicants to solve. GCHQ have a history of doing this sort of thing, and this is their latest incarnation. It should be obvious to any computer science student this is hexadecimal, a numbering system frequently used in computing. The question is, what do the numbers mean? My initial thoughts are that it was some sort of substitution cipher, but if one looks closer you can see a number of interesting clues. The first is EB. EB is machine code for jump. Jump means take the execution cycle to somewhere else in the program. If we look over here we can see a dead beef. Dead beef frequently refers to a deadlock or software crash. And finally down here you can see 90. 90 is the machine code instruction for do nothing, frequently found to introduce delays and things like that. So we can theorise based on these facts that this may in fact be a computer program. To test our theory that this may be a computer program, we need to copy and paste or type out this entire code into a file on the computer and run it through something called a disassembler, which converts these raw machine code instructions into something which is human readable. So I've currently typed this. I click on this one and look at part1.bin in a hex editor. So you'll see that the code here on the left hand side ties in directly with everything that's been typed on the Can You Crack It website. So I'm going to run this file through a disassembler. The one I'm going to use is the NASM disassembler. So NASM disassemble, use 32-bit mode, and disassemble part1.bin. Now this immediately processes the binary file and converts it into assembly language. Now the question is the code actually machine code, or is it something else altogether? So to establish this, if we look through the code we can see that every instruction disassembled fine, there's no errors, so we know that what is present there is valid machine code. The question is, does it do anything useful? If we look through the code we can see first of all there's that jump that I was talking to you about. You quite often see that at the beginning of programs to skip over some initial data or something along those lines. In this case it's these two lines here, which I'll talk about a little bit later. There's that dead beef again. Well, this might be an encryption key. If we scroll down a little bit more, these two lines here appear to be some sort of sanity check. So to actually figure out what this code does, we need to go through and analyse each line one at a time. So I'm going to open it in a text editor, and the initial steps I'm going to do is, in this case we jump 6 instructions forward. Well, that's not very readable for a human being, so I'm going to change these to be labels. So I'm going to say jump to start, and then at location 6 I'm going to put a start label in. If we look here, there's a couple of instructions just there, and here's another jump if not 0 to position 0xe. Well, that's here. Well, this looks like a loop. There's an increasing variable there and we're jumping back until it reaches 0, so let's call this label loop 1. Jump if not 0 to loop 1, and so on, and we go through this code repeatedly doing this until we reach the end, and then we go and look at each section and try and comment and figure out what it does. So obviously I've already done this. It took about an hour or so. And we're going to look at part1 clean.assembly and open it in a text editor. So here's the code which I've gone through now, broken up all the code and put comments in to explain what I think different parts do. I've added these 2 additional lines at the beginning. These are just so that we can run the code later on. So now, having a look at the code, there's that jump that I said about earlier. That's the very beginning of the code. There's then 2 instructions which don't appear to be used. In fact, you'll need these for stage 3 of the challenge, but not this current stage. If we look through the rest of the code, there's also, right at the bottom here, 4 instructions which never get executed. The program execution sequence never gets here. So there's a question over what they do or what their purpose is as well. So if we scroll up and go through it step by step. So right at the beginning of the program we allocate 4 kilobytes on the stack. This is the stack pointer, and we move it up or back, whichever you wish to prefer to call it, 4 kilobytes. We then find a loop here. There's that loop I was talking about right at the beginning, and it takes the first 256 bytes of memory and fills them literally with the numbers 0, 1, 2, 3 up to 256. Now that immediately raises the question, why? What is the purpose for that? Well, anyone who's familiar with RC4, one of the encryption algorithms, you'll recognise this from the very beginning. If we go onto Wikipedia and look at the RC4 algorithm, RC4 is what we call a stream cipher. It produces a stream of numbers, and we XOR our data with this stream to produce the cipher text. And the very first part of the algorithm is the key scheduling algorithm, and you can see right at the beginning here, here's a loop, and it fills 256 bytes of memory with the numbers 0 to 255. And then immediately after there's another loop. So just to test our theory, let's look at the code. There's the first loop. Now if we scroll down, here's a second loop, and if you study it in detail, it does more or less the same thing as this bit here. So we can theorize now that this is the RC4 algorithm. The question is, what is the data, and where is it coming from, and what does it contain when we decrypt it? To figure that out, we're just going to follow the code through to the next step. So the next instruction is jump to label 1. So we scroll down, I've labelled it down here, label 1. There's those two instructions which don't do anything that we saw in the code on the website, and there's a call made back up to the top. Now normally a call is followed by a call, do something, and then we return back to the next place in the program cycle, if you like. Now if we look through the code, we see there's not actually a return. So there's a question here: why do we jump first to this position and then call back to another position at the top? Why not just follow the execution cycle through and run the code to begin with? Well, the clue here is that when we call a function, we push onto the stack the location of the next instruction after the call, so we can return to it later. So let's go up and have a look at the decrypt function here. Now we can see we store the stack pointer. This is that key stream location which we generated earlier in these loops up here. And then off the stack we take a memory location. Well, that actually is the memory location of the next instruction after the call. That's the memory location for this point just here. So remember I said there's these 4 instructions here which are unexplained. Well, the memory location we're now storing in the ESP register is for this location here, right before these 4 bytes. Then there appears to be something called a sanity check. It's checking that the memory location we've got is in the right place. It takes the next 4 bytes off the stack and compares them with 0x41414141. And if we scroll down, these 4 instructions actually compile to 0x414141. If we look at the code on the GCHQ website, there's the 4 ones. So we're checking that we're actually at this location in the memory. And then it takes another 4 bytes off, so this is going to be pushing us beyond the end of the program to this point here, and it's looking for 442s. Well, obviously they're not there because we haven't put them there. So the question is, where do we get them from? So there's some missing data here that needs to go at the end of the program or somewhere that it's expecting. The next section of code copies a handful of bytes from the end of the program into the stack into data memory. The reason it does this is because memory in the code isn't normally modifiable, so if we put it into the stack we can modify it. In this case we're going to decrypt it and actually produce the result. Once we've got the data to decrypt into the stack, this loop here runs through the data, decrypting it against the key stream which we extracted earlier, and this last bit of code here makes a call to the operating system just to terminate the program. So the question now is, where does this data come from? Where are we going to get it from so we can actually decrypt it? I've posted a little image demonstrating how things are working. So this is program memory. This is the code here. Is this part here, the main program code, and then immediately after that we've got some data which is expecting to decrypt. Once the algorithm starts running onto the decryption, I said it copies this, the data to be decrypted, into the stack, and right above that we've already got the key stream which we've already produced, so we're going to XOR this key stream with this data, and at this memory location we should find the decrypted data that we can then extract and figure out what it says. So where to find this data from? Well, if we look at the Can You Crack It website, this here is actually an image. There's no text here, we can't select, copy and paste it. So if I right click on this and save it into our directory here, that gives us the image file.